Okay. So now we have kind of covered what we did previously in a more generic fashion. We also extended a little bit by doing how to do variable forgetting. Now, the next thing, or one next thing to go for, would be the so-called pseudo-linear regression. Now, what is the difference? We have done autoregressive and ARX models using this framework. It works fine. But if you have a moving average part, we cannot do this because the epsilons depends on the parameters estimates. So you have been creating those epsilons in some cases in the assignments or in the exercises, and thereby you can see that it depends on the parameters. So thereby it's a nonlinear optimization effectively that you want to do. That leaves you with two options. Either you do the nonlinear optimization or you rewrite it in a way so you can do pseudo-linear regression. This is, you can say, what has been taken to an extreme extent in the Marima package. That is basically a pseudo-linear regression approach that's happening in there. The trick is that given some parameters, then you can calculate what are the one-step prediction errors throughout the series. Because given the parameters, you know what the errors were. You have the residuals. And now, given those residuals that you now estimated, you can then use those as regressors in a least squares regression model. So basically means that some of the elements in xt depends on the parameters. We still want to minimize the same thing. Here's just written a little bit differently. You forget part of the old thing, and then you add the newest prediction error. So the recursive pseudo-linear regression algorithm is exactly as before. The only difference is that at every time point, you need to calculate xt as a function of the previous estimate of theta. So given this estimate, what is then the state that I'm predicting with? What are the epsilons that are needed in this case from my previous? If I have an MA1, I need to estimate and have it as a predictor. I see a couple of question marks. Basically, if you have an ARMA 1,1 model, then what you want to look at is the model that looks like yt is minus phi 1 yt minus 1 plus epsilon t plus theta 1 epsilon t minus 1, right? Now, I will just take this and move it to the end, because what we want to do as a model here, to make a pseudo-linear regression model, is to say that yt is equal to, and then the parameters here are minus phi 1 and theta 1 plus epsilon t. So what we need as predictors in here, well, we can easily use the previous observation, but we also need the previous epsilon. And this here is a function of not this theta, but the theta hat that we estimate here. Does that make sense? So you have this epsilon here. You need to do that, to have this in order to make the regression. In order to make this update here, you need to define xt. And that xt is this. And this over here is theta hat t minus 1. Or it will be t when you update it. plus epsilon t. So that's what you're looking at, that all of a sudden you have some of the residuals back in time. You're looking at time t, so the residuals back in time, you can estimate those. You can calculate those when you have an estimate of the parameters. You've done that. So you can do that, but every time you have an update of theta, every time, then you have to update, you have to kind of estimate this at each time step. Yes? Well, that is the one that is available. So that is t minus 1. It's one after you got the last observation. So that it is a prediction that you had. So now I think it's the time to go and show you how things work. So I'll take the Vex example from before. First, just read the data. Make this a little bit larger. So here have the temperature data. What I did here was to aggregate all the data on an hourly basis, just to make things, the calculations faster. Oh, sorry, a daily days. I use the J data up here as my reference. And the heat consumption. And then if I do a linear regression model for the heat consumption as a function of the temperature, the ambient temperature, and then I plot lines for that on top of that, where I flipped the order. So I used, as in the figure in the slides just before, those were the hourly data. Here I have the daily data, but you can see how good the fit is. Now I have my own recursive least square algorithm. Basically just initializes first, and then to store all the results I'm saving, I make it a store, give it some names that are appropriate, and then this loop down here is effectively what goes through and does the recursive least square with, and at first, a fixed lambda. So if I do this, then what I get out are, you can say, the data that comes in, the errors, once the prediction errors, the estimate of the theta, and the lambda value that is currently used. At first, these lambdas are of course fixed because I fixed lambda, but I will make another version later, and then I want to have the same structure. So if I plot at first just the prediction errors, and then my intercept over time, and my slope over time. Here I was using 0.9 as lambda. That corresponds to using 10 days. So it's not too far from the 8 days that I used for the hourly data. And you can also see that the results look sort of similar to before. And you also have this dip here at some point in the middle. And you can see the reason for that. You have some very large residuals up there. But now, first, I just picked a lambda. We want to optimize this. So what I will do is I will have this objective function that runs the before mentioned algorithm, and then what it does is to return the sum of, well, first omitting the first 50 observation, and then just the sum of square prediction errors. And let's just calculate this for a lot of lambdas and apply that, and then let's make a plot. So it looks like this. It looks like the optimal value is around 0.8, but we can just optimize it and find out that it's actually not just around, it's very, very close to 0.8. So if I use the optimal value and do the same plot as before, it's not so different from what we saw before. Now 0.8 means I only have a memory of 5 days. But you're looking at something that minimizes the sum of squares. So what is actually happening? We have a few errors out here. We have an error, have a large prediction error here, and then we notice that that is the same time as where the slope estimate is just changed dramatically. So I'll just take out those rows where the estimated slope is less than 100. So those are days 210 and 211 in this data set. And if we just look at a few more, oh, I hit wrong key. Let's look from 205 to 215. So the ones that we saw were odd are those two there. How are they different? Actually, it's only the first one that is very different. Because the heat consumption here, the temperatures here are about the same 5 days in a row. So the expected heat consumption should be about the same. But then you have one here where you use roughly 10% more. And of course, that will give you a large error. The prediction error here is 600, roughly. The square root of that, 25. So that's the prediction error. It does all that it can do to minimize this particular prediction error. If you look at the objective function, oh sorry, the prediction error is 600. If you go back and look at the objective up here, it's roughly 2 million. Now, if you take just this observation here, 600 square, what is that? $300,000. And if I compare that with the combined objective function that was 2 million, that means that this particular observation gives you 1/6 of all the weight in the prediction errors. So this is the one, everything, all the other prediction errors here are so small relative to this one, that all it's doing to adjust the lambda is to find the one that fits this one good. Everything else has less importance. This is also the reason why you want to do optimal forgetting, or do variable forgetting, because you will have these weird things happening, and you want to get by that. If I do the same thing on an hourly basis, it's just taking the hourly data. Here the calculation time is a little bit longer, but it should converge, or not converge, get true. Here we see that the optimal lambda is actually rather small. Again, we'll just optimize it. And we get something that is roughly 0.5. And if I run the algorithm again with that and do the same kind of plot as before, then you can say again here in the middle, you'll see some larger residuals, and you'll see that the intercept here is jumping up and down, positive, negative. So this is not something that you actually want to work with. It's not behaving nice because the lambda is so small. And the lambda is small because there are some prediction errors that are large. And then it tries to reduce to fit that one better. And that typically means that you end up with a very small lambda. But again, it's some few prediction errors out here that are driving the whole thing. Now the sum of square prediction errors here is 44 million. But also we have 10,000 points, roughly. But we see that we have a handful that are of the order of 500. So each of these points gives 250,000 towards the 44 million. if we do the same thing with a variable forgetting factor with the one that I showed, set the minimum to be 0.5, and I just picked a not too random target. I do it on the hourly data again. Well, at first it looks like something not too different, but notice the slopes doesn't get very, very small anymore. It was down at minus 100 and some before, and now it's minus 80, and that's more close to what the level is at the time. If you look at the lambda over time, this is what I get. And notice in particular the dip here at around 200. I set the minimum to be 0.5, and it actually goes down there. So at that point in time, with that observation that it's kind of odd, it forgets pretty much everything, and then it restarts the algorithm effectively. Now, when you look at this, do you like this lambda? Well, the average value, well, the optimal value was 0.8, but the average value that is being used here is 0.95. So it's most of the time you're actually keeping a lot of information, and then occasionally you have these dips. But you also have a quite noisy part up here because the next lambda depends only on the previous residual squared. So that's one of the reasons why, at least some years ago, I was working with, can we make this in a nicer way so we don't just update it fully based on one observation, but we do kind of an averaging out, smoothing out of the lambda as well, keeping track of what is the optimal, basically doing an optimization, Newton optimization of the lambda at every time point that's going on. So effectively, it's only 16 observations that are below the optimal value from before. But now I'll show you something. This is an old presentation. So the notation is almost the same as what I've shown today. This is the recursive least squares algorithm as I presented it in the last version, where you avoid the inversion as well. So that's the way it's implemented. And then if I want to do a Gauss-Newton update for the lambda rather than just this simple equation, then I just add 4 more elements down here, keeping track of, you can say, a Hessian. So, but if you look at this, there is some smoothing, exponential smoothing of some variables in here. I won't go through the details, but I'll just show you how it works out in the end. If you do a fixed optimal value, it's somewhere up there. Pretty much cannot see it. If you do a so-called steepest descent, which is not too different from what I just used in the other case, you get these very sharp dips. But if you do the Gauss-Newton recursive least squares update, you don't get the dip to be as large, because even though there's one prediction error that is bad, it will lower the lambda, but it won't kick it into the grave. And then it will slowly climb up again. So it's much more stable and stationary what happens up there. Then you can say, the challenge what I did was to say, well, when you hit this barrier of 1, which it does, some of these algorithms, then what happens is that you get infinite memory. But that's not what you want. You don't want it to get easily to 1. You want it to kind of navigate somewhere in the neighborhood. So rather than just allowing it to be working on lambda, I used 1 minus exponential of some tuning factor, and then I worked on the g instead. Because then the g could run around in a non-confined space. It just has to be such that this doesn't get negative, then we're just fine. And then if we, for different values of this parameter, I can get, you can say something as spiky or less spiky. But it will still tune itself to the optimal value. So if I use a rather slow method here, it will just tune to a almost stationary lambda. I don't have to do the optimization up front. I can just let the algorithm run, which is one of the nice things. But that was just to kind of give you an illustration of what you can do beyond this. I don't expect you to do this. And if you go back on the hourly part here and run the recursive filter with variable forgetting, well, you can see that the worst of these residuals up here are gone. You still have some wiggling parts in here, in particular in the slope, but it's not as bad as before. If you look at the lambda, we again see a lot of these dips. But here you can see that you have these dips all over the place. So that means that every other time you're forgetting a lot. And then you're not forgetting. And then you're forgetting a lot. And then you're not forgetting. So even though the average forgetting factor here is 0.98, then you are actually forgetting quite a bit. Nevertheless, because it's so frequent that you forget a lot. That's one of the reasons why I dislike this algorithm, but it's the most simple one to implement. That's the one thing I like about it. Because what I have here, I don't want you to do this as a small kind of 5-hour example. That would not be fair to anyone. I can say it took a little bit more than 5 hours to derive it. And then, of course, here you should also consider tuning. Oh, I think I'll just add an extra plot here, just to illustrate how often it goes down. So here I have just 100 samples, and it dips quite frequently. And then it goes up to something close to 1, and then it stays up there for a while, and then it dips again. And of course, you could pick a better value for a 0 in this case, but this was basically just to illustrate what is the consequence of doing these variable forgetting factors. You have to think of what you're doing. You have to think of how large prediction errors can actually occur at random points in time, and what is the implication of that? What is the implication of all of a sudden you're running with something that is close to a memory of 50, and then you say a memory 5. You cut everything down to only keep the last 5, and then you kind of go back up again and run it around 50 as memory. Mentally, it's hard, I think, to see what is the effect of this. But that is life sometimes. So you cannot, you can say having 50, converting 0.98 to say that is effectively 50 observations is not fair, because you only had 10 observations with that value. And then prior to that, you forgot everything. So effectively, you have 10 observations at this point in time here. So the 1 divided by 1 minus lambda makes sense when you have the fixed lambda all over the time. Here you would have to kind of keep track of what is the effective memory. What is the sum of all previous lambdas multiplied in? Okay, so model-based adaptive estimation. We're going to do a different approach right now to do the adaptive adjustment by doing something that you've also seen before. So when you look at this setup up here, I hope you'll recognize it. Because at least some of you have spent quite some hours making something similar to that work, right? So basically, this is a Kalman filter where the A matrix is just the identity matrix. So it's just the same as before. And that means that you know exactly what to do if you're going to use this. if you are giving a matrix C and some variances, you could do this, right? Or at least you know what you're supposed to do, if you haven't done it yet. Now, what if we, instead of using the state x, we just label that theta? So now we say that the parameters are following this process, and then what we observe is basically just a linear regression model where you have some stochastic parameters. Does that make sense? Now, look at this down here. You take make the reconstruction of the theta by taking the previous estimate, and then you look at the one-step prediction error, and you have a gain on that. Well, that's the same thing you do in the Kalman filter. So it is quite close to what we've done in the recursive filter down here. It's just different because of the sigma here. What is the implication of this difference? Well, basically, in the recursive and the method, you do not forget anything. You just update your estimates. Whereas in the adaptive, you forget all parameters are forgotten in the same matter. What you have here is that by picking the diagonal elements of sigma 1, you can say, well, how much do I trust the individual parameters? It's something that I actually quite often do for model development, is to add, if I have a Kalman filter running, I add an extra state for an unknown parameter, and then I see what is my estimate of that state. Typically I do it in a nonlinear version of the Kalman filter, but just to say, that's an easy way to figure out what is a good estimate of a parameter, what is happening. Is it changing over time, or is it fixed? So you can use the Kalman filter as a different approach to track parameters. And that's basically just stepping back to chapter 10 and redoing the Kalman filter. You can also have, well, models where the parameters are time varying. Now, in the Kalman filter, we know how to formulate the ARMA model, but we cannot do it here. We're back to the pseudo-linear regression here, because the parameters are still, the system equation is just for the parameters, whereas the observation down here should have these as knowns. So you can, in this setup, if you have a parameter where you don't allow any noise, you don't have any random walk in the parameter estimate, so you can have some being deterministic, some being fixed. But when we have these parameters that are stochastic processes, we call the model as such a double stochastic model, because you both have the noise in the observation and you have the noise in the parameter evolution of those as well. So it could be also that now, in the previous slide, I formulated just a random walk process for the parameters here to make it parameter estimation. But you could, in more general setting, have, say, an ARMA model for how is the evolution of the parameters. But you could also make that as a Kalman filter, as long as it's an ARMA structure for the parameters as such. Now I will change to, you can say, things that are outside the scope of this course, just to give a few outlooks into what else is out there. Now, if you look at this signal, 10,000 samples from something, a process, and this is just one, just because it's very different from what you've seen so far. That's pretty much why I picked it. It's a process that stays in the neighborhood of -1 for a while, and then at some point, at random, it changes to a state near 1, stays there for a while, and jumps back. And the duration of these periods is not fixed. the formulation, this model, this is the definition of the model. It's defined in continuous time. All we've done so far is in discrete time. But this model is formulated in continuous time. For now, well, this W out here is so-called Brownian motion. How many of you have heard about Brownian motion before? Just more than I expected, I would say. So, and the tuning, the noise part out here, in a discrete time setting, considering this here, you can solve this equation by just doing a small delta t. And then the Brownian motion part out here, dw, can be just simulated with a Gaussian random variable and standard normal. And since the sigma here is outside, it only depends on the sample time, the variance of that. So consider this out here just to be white noise. But Brownian motion is just white noise in continuous time. Get back to a little bit of mind-boggling facts about that, but that is what's happening. And then the equation here is basically you have a minus xt, and then you have a xt plus 1, and then you have a xt minus 1 term. Well, what does this mean? It means that when you're close to 1 up here, this is effectively 0. If you're close to minus 1, this is effectively 0. And then there's a term that tries to get you towards the center. And it's some noise. So it's basically a process that if you're close enough to 1 or minus 1, you stay where you are. And then occasionally you get a kick that is large enough to make you jump to the other one. That is what's happening in here. Now, Brownian motion, as said, is the continuous time counterpart of a random walk. Now, here are just some examples. And when you just look at it, you cannot distinguish this from a random walk process. Now, here comes some of the facts or properties. A Brownian motion is continuous with probability 1. But when you take a time step forward, you always have something that is normally distributed. And the variance of this, as mentioned before, goes with the time. So the shorter the time, the less the variance. But it's never 0 unless the time step is 0. And then you haven't moved anywhere. And well, what that means is that it's nowhere differentiable with probability 1. So we have a continuous curve that is nowhere differentiable. I don't know of any other curve that is like that. We tend to treat them in discrete time, then it's just a Gaussian increment that we look at. That's also why in the definition of the process here, I have the dw. So I look at the change in the Brownian motion, not at the value of the Brownian motion. So this means that if you want to straighten out this graph over any interval, the length is infinite. So, have any of you heard about something that is similar to this before? From a different part of math? Some of these properties are actually, you can find that in other, yes? Yes? Sorry? Okay, I don't know.
You can just, as absolute value, it has 0.
Yeah, you have functions where you have points where it's not continuous. Okay. I must admit, I don't know the one. What I was what I was thinking of is basically fractals.
Yeah, it's a fractal curve.
Okay, so it's a fractal curve. Okay, so then we are just different names for the same thing. That has happened a lot in history. Yes, so fractals is one example where you have this happening. I don't know how many of you have made fractals. I think the easiest one to just give you an illustration would be the one where you take a line, then you subdivide it in 3 parts, then you keep the outer parts, you take the middle part and substitute that with this here. So you do this, and then you reiterate this, which means you take out on each of the subparts, you take out the middle third, and change that. And if I started out with a triangle, I will get close to a seasonal greeting soon. But if you continue doing this an infinite number of times, soon it's too small here, and I cannot draw it much nicer than this without using too much time. Every time you go one step further down, the length from here to there, you multiply by 4/3. And then you take this and do that an infinite number of times. Then you have a number that's greater than 1. You know how quickly this goes to infinity, right? You call this as a fractal dimension 4/3, but that's another thing. You don't do the same thing for the Brownian motion, but you actually have something that is nowhere differentiable, infinite length, and still continues. Another example are so-called stochastic differential equations, which is more, you say, general way. Basically, the equation that I showed the simulation of before is a stochastic differential equation. Due to the property of the Brownian motion part, it also means that what you learned back in high school, how to integrate, you just took intervals and make them more and more narrow, and then in the limit where the difference in x or time was 0, you converged to the integral. And you could pick either the left-hand value or the right-hand value of the interval or the middle value. It always converged to the right number. You may not remember that, but I'm sure you've all seen that back in high school. Now, for a stochastic differential equation, if you want to solve that, you get different values if you pick the right hand and the left hand value when you make the integral, the time step, go to 0. So therefore, there are different implementations of the differential equation all of a sudden. The typical ones are the so-called Ito integral and the Slatonovich, but that's a totally different course. But generally, you have definition, you have something that you have some drift, you have some process going on by some function of, well, also function of parameters, of course, of the state and time, and then you have some diffusion, as in how does the probability mass just disperse due to the Brownian motion part. Effectively, you write it as an integral equation. So it's a stochastic integral because you have a stochastic integrand. So that's the topic of the course 024-25. That's a kind of, this is the core of that course. Just a quick mentioning for those with relation to finance, co-integration of order 1 is basically, if you look at these data here, you have one series up here and then you have another one, and if you kind of compare the two, you'll see that they are somewhat related. So if I take the second one down here, and rather than just showing the second one, I'm showing the second one minus 1 minus 2 times the first one, then I get something that is just white noise. So those two series, the original series, are co-integrated because they kind of depend on each other in that way. And if you want to read more and know more about that, well, it's also enough to get a Nobel Prize if you're good at it. But I mean, we shouldn't all get that. Then it'll be too custom. So, and here's also the what's called motivation for the Nobel Prize. And a few more links to a lot of different things that I didn't mention. I think particular what may be interesting is the spatial time series. Often you don't just measure something somewhere, but you measure something at a number of places. If the number of places is huge, all of a sudden you need to kind of take care of that. You cannot just treat them as what happens with the temperature here and there and there. You have to kind of go into and say, well, what would be the right way to represent the spatial properties? And if you at the same time go to continuous time, then you have potentially a stochastic partial differential equation. Those are not nice to work with, I can say. You can do some things with some, but in generally you cannot do too much with that. But I mean, of course, there are cases where you can do things, and there are cases that are more complicated. Finally, just some comments on related courses. I mentioned the 24-25, diffusions and stochastic differential equations. The focus of that course is basically on what are the properties of stochastic differential equations, how to work with them, how to simulate them, how to do things with these things. And if you go back and say, well, what I've said many times, we have been working in discrete time because that's where you observe things. But to describe the process, it's often easier to do it in continuous time. Which is also, you can say, in the advanced time series analysis course, there's a lot of continuous time actually using the SDE approach from here as a modeling tool. So combining what's called an extended Kalman filter, where you have a nonlinear representation of the system, and then you have observation system of that may also be nonlinear. And then you basically just take the ordinary Kalman filter and linearize it and do the same thing. If you sample frequently enough, everything works out fine. And another course that is also, you can say, a stochastic process course is the 02407. That's quite different from the other two. But the first two, everything is in continuous time. And it's also, it's a continuous state space. Almost everything. Whereas for a stochastic process, you're looking at jumps between different states. So you have discrete states. A classical example is in the financial industry. You probably all heard about countries where the rating has been changed. Not so much recently, but at least a couple of years back. Many countries have a AAA rating. You can go down to AA or an A or B. And also for companies and for individuals, I don't know how many of you have a credit profile that you know of, but having lived in the US, I mean, everyone having a credit card there, you have a score, depending on, do you actually pay what you're supposed to? How do you spend money? How do you do things? So you have a credit score. And your credit score is not good enough, then you cannot get a loan, for instance. It's not dealt with exactly the same way in Denmark, but there's still the same thing. But you jump between different rates. And not all jumps are equally feasible. So how to do that is one thing in there. And of course, there are many more courses that have some relations. You all come with very mixed backgrounds. And you can say for each of your backgrounds, there are courses where you somehow touch upon data that is sampled over time. I expect, or I postulate, at least. But today, I think what I wanted to do was to say, well, you have the Kalman filter. You can also use it to trace parameters in models, and even make models for how the parameters evolve over time. But you can also write it in some cases as just an adaptive recursive least squares algorithm. Again, it depends on the application, what is that you need to know. And you should pick the tool that you feel this is the easiest way to get through to get the job done. And then I just came with a few comments on what is else out there. Continuous time, nonlinear models, and in particular SDEs. And with that, Merry Christmas. I must say, I did not make this hard, but a colleague of mine did that. And when I saw it, I was like, okay, I have to have it. So thank you.